Okay, so today I'm going to talk about oscillations of magnetization in a ferromagnet. First, I'm gonna give you the outline, and then at each step you can ask questions about the system. So let's see. In the beginning, we're going to talk about a ferromagnet in an external magnetic field. We're going to determine the energy of magnetization of the magnet, and then try to relate this energy to a Hamiltonian in generalized coordinates. At the second stage, we're going to discuss the system with no external field, and we're going to be interested in the fluctuations of magnetization as a function of position, and try to determine an equivalent Hamiltonian, which will turn out to be the same as the Hamiltonian of harmonic oscillator. Okay, I already underlined some parts of this slide, but what we have is a ferromagnet in an external magnetic field. The field is along the z direction, and at first we're going to look at small region with uniform magnetization, or so to say, the magnetization is independent of the position, and we know that the magnetization is normalized to 1. Okay. Moving on. From this state of uniform magnetization, we can assume small deviations from the z-axis. And at first we write the exact energy. Let me again underline what I'm talking about. So the energy, excuse me, I'm not so good with this writing. Here we have the energy in yellow. And because the field is directed only along the z direction, we write B times mz. And we know that the norm of this magnetization is 1. We use the fact to express mz as a function of mx squared and my squared here. Now the next thing is we have already assumed small deviations. So to assume small deviations means that mx squared and my squared will be small. So we end up with the following form. We have a constant term, and this is done by just Taylor expansion of the square root of 1 minus something small. Now, in the next question, we're asked to relate the equations of motion of the magnetization in the x-plane and in the x direction and the y direction to a generalized coordinates, such that the equations of motion can be written in the following way. So the dot represents the time derivative of the magnetization along a certain direction. We have the magnetic field, and as you can see, it seems that they're cross-related. X is related to y, and y is related to x. The time derivative of x is related to y, and the time derivative of y is related to x, mostly. Now, in order to determine the Hamiltonian generalized coordinates, one can do the following. The Hamiltonian formulation is easy to write, and I hope everyone knows the equation. If not, I can write them down. But one of the equations would be the following. We can first identify the generalized coordinate and momentum here. So the generalized coordinate will be mx, and the generalized momentum would be my. And if one writes down the Hamiltonian equations, here I wrote already just 1. So the derivative, the time derivative of mx is going to be the derivative of the Hamiltonian with respect to my. One can write from this equation, one can replace here the time derivative. So we have b my. And if one integrates, then one can obtain, h, for example, here below, that is equal to b times my squared 1/2, okay, plus plus some constant c that depends on m of x here below, because we have integrated only with respect to my function that depends on two variables in principle. So one can derive the Hamiltonian doing the same thing, but for the derivative, the time derivative with respect to my. And as you can guess, you would obtain a quadratic Hamiltonian. Sorry, let me see. Where do the equation of motion come from? In this case, they are given in what the problem describes. So if you're referring to those equations here, I'll read out the question first for everyone, because maybe not everyone is looking at the chat. A question was asked about where do the equations of motion come from? And in this case, yeah, they are given in the problem. Okay, so one can determine the Hamiltonian, which will be a quadratic dependence of my and mx, plus of course a constant that would not matter, because you can always shift the energies. And here just, yeah, this is the Hamiltonian, of course, with this, with the following replacements, like q and with p here. And of course, if one does this, we can work either with q and p, or we can work with mx and or my, but we have a quadratic Hamiltonian that seems to have the form of the harmonic oscillator. Okay, well, here there is the correctness check, but I show you very quickly the equations of motion, if you don't remember them, the Hamiltonian formulation of classical mechanics. Okay, so now we're going to move to second part, when there is no magnetic field. Are there any questions or something that was unclear about this stage? You can ask me now. So if not, at the end. In this part, we're going to be interested in magnetic field, that the external magnetic field will be 0. And we're going to look again at the magnetization, but this time the magnetization will not be uniform. We'll assume that it varies as a function of the coordinate, or its position in the ferromagnet, meaning that if the magnetization depends on r here, then also the energy being dependent on the magnetization will depend on the space coordinate. Of course, we know that the minimum is given by the uniform magnetization, and we're going to be more or less interested in how are the fluctuations of the energy dependent on the magnetization. So here I know that the energy should be invariant in the rotation of m, which is, I think, quite intuitive. And it was given, so this is given as one form of the energy that one can think about. In the problem is just a constant of the energy. Of course, now we're dealing with continuous variables, so we have an integration. The magnetization is no is now a function. So every coefficient in this vector of magnetization is now a function that depends on R. We have a 3-component vector that depends on 3 variables. Each component depends on 3 variables. So this is a vector field, 3-component vector field in 3 dimensions. And here it's just the form of the energy. And of course, we sum over all components and all variables. What we do is the same exercise. We write the mz component. So this is the explanation of the step, by assuming that the mz component is small, that the fluctuations happen in the x and xy plane. We simplify the energy in the following manner. So again, with the same trick, we write mz, which will be now here's the expansion of the square root, and we neglect all the terms that are of this sort. So finally we end up with the following result. This is assuming that the deviations from z of this are small. Now, in the next steps, will be try to introduce derive the Hamiltonian for the harmonic oscillator. And as I hope you all remember that for the generalized coordinates P and Q, one can write the ladder operator, so the creation and annihilation operator, and yes, as you can see, it's the same scheme. The m plus minus will introduce 2 different operators that will relate mx, that will be linear superposition between mx and my. And we write them in the following manner, quite usual. Sorry, let me not use yellow here. Red. Mx is here, and then my here. Again, this is just a linear transformation between the m plus and m minus, so mx and my. Then if we replace in the previous formula mx and my, here, we use the same formula that we found before. What we do is we can express all terms. So by replacing mx here, we square it. We have a plus sign here because it comes with a plus. And here we have a minus sign, it comes with a minus. And because my has 1 over 2i in front, it has a minus sign. So in the end, I think it's quite easy to notice that, for example, this term will disappear, this term will disappear, all the terms will disappear that are squared, and we're going to be left with only the cross terms here in green. We have a minus sign here in front, so, and 1/4, so in the end we're only left with the final result, which is here. So the derivatives of m plus and m minus with respect to the space coordinate. Now, one way to, here, for example, at this stage, we cannot say that this is somehow representative of a harmonic oscillator. We know that they must be somehow related because we saw it in the previous exercise. What is the next step is to introduce, here in this step, we introduce the Fourier decomposition of those operators m plus and m minus. So now, quite clearly, just 1 over the square root of the volume of the system and the sum of exponential of mk. Now mk has a k has a discrete index, and so we have those two expressions for m plus and m minus. We can then easily calculate the derivatives of those two, taking the derivative with respect to a component or a variable r beta is quite easy. There's just k beta, the component beta of the component. So we have the component beta of the corresponding k vector in those two expressions, with the main difference that there is there is a sign difference between those two. And once we have taken the derivatives, one just replaces the two expressions that we have found previously for m plus and m minus. So here from the previous two expressions, m plus and m minus, here's the volume, the sum over beta, the usual integral over O space, the m plus and the m minus expression. Then we put everything together. We have now the sum over 3, k prime, and beta. And in the integral, we have two exponents that depend on r and on k and k prime. Okay. Now the next step would be just to have this expression and recognize that this is going to be proportional or even equal to a delta function. I'm so bad at this. Okay, you get it? It's going to be proportional to a delta function of k and k prime here. Of course, there is the volume in front, integrated over O space. And now I think it's very evident that one can replace k with k prime in the sum. One of the sums will disappear here, and we're gonna end with a single sum over k and a single sum over, so a single sum over k and one sum over beta. Once k is equal to k prime, one can combine them into k squared beta. And here, as you can see, this is, you can write it also as the norm of k squared, as I write below, actually, yes. And so now, what can we say? How is this related to actually to the harmonic oscillator? But that's here, as you can see, we have mk, okay, complex conjugated, and mk. So this is very much similar to so those fluctuations of the Hamiltonian in the xy plane is a sum over all modes k. And yes, you can see every mode is weighted with k squared, and then it's like mk indicates the strength of this mode. So with that, I would actually like to conclude this short presentation and ask you if you have any questions. One of the questions that was asked is, could you extend the first Euler approximation with the extra term, or is that too complicated? Just a second, I'll answer one by one. You can write them now, but so the first Euler approximation with an extra term, you mean not to extend to first or not to to first order, but to go to second order. Indeed. I wouldn't say that having just a second order would be complicated, rather than the equations of motion I would expect, naively, I would expect that in the Hamiltonian there will be a term that is to the power of 4. I guess if one expresses to the next, yeah. So to answer the first question, I don't think it's too complicated, and naively I would expect that the Hamiltonian will have a power of 4 of my and mx. Then later that would be a different potential, and you can probably solve it. A funny, interesting thing, if I'm correct, you can probably solve it with perturbation theory and treat to the power 4 terms in perturbation theory. But I don't see, just an expansion is not too complicated to answer this question. Is this okay? Now, next question is, can you go back to the slide when you write with the H in terms of P and Q? Yes. So H, here is H in terms of P and Q. So I'm expecting you to ask a question now. Okay, you understand now. Okay. Then we move on to the next question. In one of the previous slides, you say E is equal to E dm dr. Is this always true, or this is given in the exercise? Suppose you expand the energy to first term, then you have to expand. I guess this is a very short answer, but if you want the minimum energy is at m constant, then if you want to expand the energy to first or second term, right, the first term should be 0 because you have found the minimum, and then the second term will give you the fluctuations. So if you expand this energy to second order, then you would obtain this dm. You would have the derivative of m with respect to r times a second order in derivatives. Okay, and Yuli asked me a question: what are the frequencies of the oscillations? The frequencies of oscillations. I would say that the frequencies are k squared. So it oscillates, I mean, oscillations as a function of coordinate or in time. Here we only have coordinates, so I would say the oscillations are given by k squared. First, Yuli, did I answer the question? Before I move on. So a bit more precise, right? Dimension. I guess if one write it as h bar omega, then it should be the frequencies should be c k squared divided by h bar, let's say. So it's a quadratic dispersion of those modes in K. Okay. So in slide 10, how did we get to the delta function again? Just let me answer this question very quickly. In slide 10, the definition of the delta function here, this is just the definition of the delta function. Sorry for my writing, I'm not so good at this yet. So we have the integral over of dr of an exponential here, of an exponential of minus, it's just the definition of how you get the delta function. Minus, yeah, is it quite clear now? K prime. That's a mathematical question. They form a basis of functions of L2 functions. So the exponentials form a basis for functions. To be honest, I don't know how to answer where does the volume come from now. Then, if anyone can answer this question. Oops. Yeah, because you have the integral over all space, but it depends on the definition. One can write the delta function without any volume. It depends if you ask a mathematical question or of the physical system. I can put all the volumes in the inverse Fourier transform, and no square root of the volume in the one of the Fourier transforms. So this is just a convention where you put your volumes of 2 pi or. Okay. Any more questions? So I guess you can relate those to the Magnus you have seen during the lecture. Yeah, okay. So those are bosonic modes. In the end, those fluctuations form bosonic modes.
All right, Hristo, very good. Thank you. If there are no further questions, let me just what do I need to do with you? Cancel the spotlight. Anyway, thank you for all for coming. The recording will be available. Don't forget, there's also a lecture on Monday morning, last lecture of this half of the semester. It will be given according to the plan. There is an announcement with a link to Zoom meeting. Good. Thank you again. See you then on Monday. Bye.